Welcome back to the course. In this lecture, we'll take you to the lab for the laboratory demonstration. Now, this process is known as parking. We are parking, like car parking, we are parking like kind of homing. So, it is parking the head at the left side, left corner of the machine. Now, after setting the G code and making all these settings, we are here to prepare the bed, for machining, okay, to prepare the bed and to set up all the things like spool, filament will filament through the rollers that would come through the extruder, and we will try to see that whether it comes properly or not. Before that, the heating is there, heating that was done, that the commands that we gave, the heating was there, the bed is getting hot, or it has come close to the temperature that was given 55 degrees, the nozzles are close to 230 degrees. So, the temperature is trying to come to this desired input here to 230 degrees for the nozzle, 55 degrees for the bed. It will take about 15 minutes. By the time we can prepare the bed. So, let us try to start the cleaning and loading and unloading of the material. This is the cutter that is being used to cut the filament, okay, if required. So, this is the tube, this is a tube through which the filament would come through, okay. It provides proper path to the filament, okay. This tube is attached to filament head. This is spatula, this will be used to clean the bed. So, this is distilled water with some cleansing agent here, a few drops. So, some of the liquid cleaner is sprayed and it is cleaned with the help of spatula. So, the whole machine head here is actually glass. So, we have to be careful. So, what is this white milky color, white milky material? It is nothing but we have used fabric, that is the adhesive material, this fabric. So, we are again applying some more fabric. So, it will help to lock the first layer. As we said before, we have put our CAD at the center of the envelope. So, that is why we are preparing the portion that is sent at the center. So, a thin coat of fabric is applied at the center. Now, this is our head, this is our, and there are heaters here, okay, that are heating the filament. The spool is coming through this tube, this white tube, the filament is coming through this white tube, okay. So, this is the head that can be moved. So, this is our X and Y movement, okay. Z movement, that actually bed is moving up and down, that movement is controlled with bed, and there are two nozzles here. The only one nozzle is active at this point of time, okay. So, let us see how to load and unload the filament. So, this is this black portion, this is a PU connector. So, PU connector can be connected, it can be screwed in and out. So, we have unscrewed it, okay. So, in PU connector is according to the size of the tube, PU connector is exactly that, the tube would exactly fit into that. So, this support. So, these are our rollers, we are taking it off, we are unloading the filament now, okay, unloading the filament. You can see this is again, this is the filament of size 1.75 mm. Now, we can see that the filament is little distorted from the tip, that is it would not enter the rollers properly. Okay, the tip of the filament or the end of the filament is not proper. So we are going to cut it. We have cut it. So it is now flat at the end or square at the end. So this is a roller. This would help to take the filament forward. When this rotates, the filament is carried forward, okay, in this direction, upward direction. Now we are entering the filament into the tube that is connected to the PU connector, and this tube is also very much according to the diameter of the filament, 1.75 inside diameter, 1.75 plus alliance. Alliance is 0.1, 1.85 mm inner dia. Now this PU support tube, the filament support tube, is connected to the PU connector. Okay. Now we will see that whether it is working properly or not. Now we will lock the PU connector. We have locked the PU connector there. We lock this PU connector here as this PU connector is locked here. So this roller that I mentioned, that is responsible for feeding, this is also known as feeder. So we are using this pulley and feeder. Two rollers, one roller is pulley, another roller is feeder. We can see that loading of filament is properly done. Now we can see that whether the filament is coming through the nozzle or not. Yes, it is coming. Now this means the temperature is now maintained. Now we will use these two clips to hold the glass with the bed, with the table bed. Okay. So this bed is at the temperature of 50 to 55 degrees centigrade. So to hold them, we use these two clips. Okay, we'll put clips here and here so that it holds, gets properly over here and at the other diagonal end. Okay, so where are the heaters for the bed? Now we can go at the bottom of the bed. Let me try. Camera would go at the bottom of the bed. This is the bottom of the bed. There are heaters here. We can see there are heaters attached here. Okay, and the base is aluminium. This bed base is aluminium. There are heaters there, and on the aluminium base, over and on the top of the aluminium base, we have put a glass plate on which the actual fabrication would take place. So it is the one clip is put here, another clip is put on the other side. So everything is in its place now. The temperatures are like we are seeing. Filament was coming out of the nozzle. The temperature is close to what we require. Close to means if we have put input 230 degrees centigrade, as we know that it wouldn't be exactly 230 degrees centigrade all the time. It might vary like 2-3 degrees or 5 degrees variation. But yes, that is the working temperature. The temperatures are set 230 degrees centigrade for filament, 50 to 55 degrees for table. The loading of the material is there. The rollers are engaged. Rollers, the two rollers means the rollers, one is the pulley and the feeder is engaged. Filament is coming properly. The bed is prepared. We have applied Fevistick to make sure that the material sticks there, and the cleaning of the bed is. So before print preview, we'll just come to manual control here. In manual control, so we are going to check manually that whether the things are moving. Oh, yes, we are checking the material is coming in, material is coming out. You can see the material is coming out. So we are manually checking whether the feeder is working or not. Okay. So the material is coming out. The extruder is being checked here for its proper setting. Again we can see extruder is activated. in this way we check that everything is quite well or not. Now, the temperature is actually 53, 230 degree. Yes, the temperature is 230 degree, 230 degrees for the extruder 1, 53.6 degrees is for the bed. Yes, that means the, as I said, 5 degree variation. I would like to correct myself. This machine is quite precise or sensitive to temperature. So the temperature 53 degree was set. So it is within 1 degree. Like 230, it might be 229 or 231. So within 1 degree of the resolution. So last thing left is we come to print preview and we start the print. Now, when we start printing, machine will go and check everything. First, it will go and check the parking place, that at the corner. So this is known as referencing. It is checking the height of the job. You can see the rotation. The Z direction is moving up, the table is moving up. Okay. So the bed is trying to touch the nozzle top, to set the 0 value. Again, you can see the rotation, the bed is moving up in an upward direction, because we do not know what is the thickness of the glass plate that we put on, and also there is layer of the Fevikwik as well that is there. So the bed would touch the nozzle end to set the 0 value. Now yes, it has started the printing. The first layer is started here now. It is now printing. It is minting. This is the brim command that we mentioned before, and brim is being fabricated before actual model. So this is the very first line that is being drawn by the machine. So it is running at the speed. So it is actually while brim, it is actually the printing only. While printing, the speed of the first layer was 40 millimeters per second. It is moving at this speed. So this part would stick with the base. Again, brim would stick with the base. This is the extra part. Okay. Now we can see here that how the feeder helps to feed the material. This is the feeder. Feeder is rotating. Okay. This is the roller mechanism here. Okay. Pulley and feeder is there. Feeder is rotating to feed the material towards the upward direction. So this is not the part of the CAD. So this is used for the deposition. So this is how the machining is happening. Okay. So this is how the machining is happening. So it will make the first layer brim that will start manufacturing the part. So the time for the machining, if you remember, was 5 hours and few minutes. It will take this much of time. So by the time the machining happens, let us try to see the different parts, different components which are here in the manufacturing in the 4i lab. Actually, we have to wait for 5 hours to see the final production, the final part. So you can see the roller mechanism closely. Okay, this is used for deposition. So it will take 5 hours for the machining to happen. So by the time, let us try to see the different components in 4i lab which are fabricated, and using rapid prototyping and other machines as well. Specifically for rapid prototyping, there are certain components. We are going to talk about a few beautiful and important features that we talked before as well, that those are produced using FDM technologies, that is fused deposition method. Now with 3D printing, that is this specific machine Tech V30, this 3D printing machine, we have produced this geometric crank. Okay, this is produced with this machine. Now this kind of hollow cylindrical job can also be produced. But this is pipe shaped with lock. Now with a locking device, sometimes we get very challenging kind of jobs. For instance, this is a propeller, this is a propeller fan. Okay, so what it does is, this you can see the number of fins here, the number of very fine fins. The gaps between the fins is very less. The angle is very important here. So this is impeller. So it is impeller, it just sucks and throws out the fluid. Okay, so here angle is very important. So this is a complicated job. So its fabrication is really complicated, really tough. So it is typical to fabricate it with any other machining like milling, turning, or the conventional machines, or maybe with CNC general machining. So now this technology FDM helps us to work freely to produce these kinds of parts. Okay, so and medical sciences, you know we have this foot. We can produce artificial limbs. For instance, left leg, right leg, and we have to fabricate artificial limbs, for instance, for a particular man or lady, and we are not able to copy. If, for instance, someone has lost its limb, he has lost his left leg, what we can do, we can just scan his right leg, and using mirror command we can produce the left leg. This can also happen. So this is artificial foot that is produced. Okay, it is actually the pattern for the shoe here. So there are certain other components kept here. So 3D printing, what we need to have the scanned model sometimes, or the CAD model has to be there. The CAD model can be produced by someone, by an engineer, or it can be even scanned model, which can be then transferred into the CAD model. Okay. So also you can see another model here. This is a beautiful feature. This impeller is a beautiful feature. You can see the angle, you can see the accuracy, really very good. So scanning helps in a way that you need to put any extra efforts for CAD, modeling, designing, putting all that in. The scanning helps in that. So this is a pen stand. This is a pen stand, and now if we need to model the same, we can scan it. We can scan it using 3D scanning. 3D scanning means from all the directions, from the different scanners are there, like different degrees of freedom, so all the scanners are there, and we have produced the similar model. So the scanning took about 2 hours, and this printing of this model took about 2 hours. So within, let me say, 2 hours for scanning, and 2 hours, maybe I will say 2 hours for printing. Within 4 hours, we can produce the same product, or we can copy the product. Okay, this is re-engineering. Like scanning and producing again. So it has produced in a very fast pace within 4 hours, like I said. So that is why this machine is also known as rapid prototyping machine. So we can produce very rapidly, just scanning and producing. That is why the term rapid prototyping and rapid manufacturing comes into play. Also, a few creative items are kept. So this is a complicated model, okay, of maybe some holy person. Okay, this is a human skull. So with scanning, we can just scan the model and produce it again. Okay. So scanners are highly capable to scan anything. Even we can scan the live humans and after scanning we can produce the replica, and same scan data can be used for printing when we scan. So white light scanners are there, like white light scanners are used to scan the human body. So in general CAD we have to draw, we have to input to the machine, and all those things are to be there. The 3D scanning helps. The 3D nowadays, 3D is a very used in engineering and mechanical background. So in 4i lab, it is a high-tech lab at IIT Kanpur. We deal with this kind of unconventional manufacturing methods. So FDM is quite possible. In rapid prototyping is very unconventional method of machining. With 3D printing technology, we can print this kind of creative jobs like this hollow cylinder. Okay, this kind of hollow cylinder. Now the beauty of these two models is that this model, this skull is solid and this is hollow. This is hollow from inside. Okay, this is lightweight and this is solid. This is quite heavy. But the beauty is that we have scanned and printed them. The interesting thing is that whatever we scanned, we got the components exactly matching the features those were scanned. So there are other machines as well, like CNC milling, CNC turning. So this is a metal part. This is a ball inside a metal cage. Okay, this is not rapid prototyping, but we are just mentioning a few components which are here. It was a cube, and it is machined with milling machine, with a CNC milling machine from all the faces, and a ball is left inside. So this is example of subtractive method, not additive manufacturing. So it is subtractive manufacturing with milling. So same kind of job we can manufacture with 3D printing. Okay, in that case we will have a support and the model materials. You know, now this is happening. This first layer was brim, and after first layer, the other layer, the second layer is now being manufactured. It is preparing support, you can see. It is preparing support here because there was an angle in the component. Now what this component is? This component is actually a key that is to be kept into the machine. A key that will be inserted and that will lock the two different parts of the assembly. Okay, you can see the machine moving. So other components are here, like we work in additive manufacturing and subtractive manufacturing both in 4i lab. So in both the mode as we work. So let us see the other parts which are manufactured here. See, all these white components are manufactured using 3D printing. Okay. All these white components are from this 3D printing. So let us see some other components or other models which are manufactured. Now this is a model or machining. This is actually the printing on the wood, that is IITK logo and the FDM Titan knife set, whatever it is, 4i laboratory, IIT. This, you know, you can see the complication of the deep features in the part. This is manufactured using the laser machine that is here. This printing, this is printing in teak ply, and we print and cut when we assemble. So this is a printing and cutting of wood. This is in teak ply. The 3D model is made. Now this is actually a very old technology. Cut and paste. There was no 3D printing and no advanced machines were there. So this was the way to develop the model. So we had to cut the faces and then assemble it and then fabricate it. But with the help of FDM, we can do this entire shape without putting any effort. So it can be manufactured directly And also with laser machine that we have, we are capable to etch and cut, as well as many materials like acrylic, wood, mica, Teflon, and so on, and we can etch and cut, both the things can happen. Few materials can be etched only like this glass, it is here, you can see it is etched here, and the image is produced. We can etch any image, any alphabet. So with these fine features and profile, the capability of machine is that it can etch and create a groove or channel at a micro level. So with this, our capacity is that we can work at micro level machining, and we can go for both creative as well as engineering aspects of job with this machine, with the laser machine. Okay. Okay, the capability or the resolution, or I can say accuracy better, but accuracy is up to 40 microns. So we can print on flat as well as cylindrical shaped jobs. Like you can see the glass, we have printed the 4i laboratory name and logo, ITK logo. So with this machine, with the roller attachment facility, we can etch, we can print, we can make a mark, we can groove, slot, or any kind of non-machining, or like any kind of non-contact machining can happen using this machine. So in general, when we say word machining, the first thing that comes into the mind is, okay, there might be some tool, some cutting might happen, contacts would be there, scrap would be produced, tool will deteriorate. But here with laser light, it comes from the source, that is and it has a non-contact method, and the light come from the source, and it hits the workpiece surface, and the material burns out, and sometimes it gets evaporated. So, and by means of this non-contact method, etching, printing, cutting, machining, these things take place. Now in this lab, we have number of machines, cutting, printing, like this is okay. This is cutting and printing on leather. This is mica. Okay, on mica, this printing is happening here. Printing can happen on this mica here. Okay, the etching on mica. Then texting on teak ply, again with laser, and cutting also is done with laser in this component. Sometimes this kind of cutting is also to be carried out on metals. Okay, this is carried out with a machine known as abrasive water jet machining. So with water jet cutting machine, we can cut any metal, any non-metal. We can see this is a marble, and this is granite. Okay, this is granite. Okay, it is a brittle material to cut. This is a Chinese dragon shape. It is cut with abrasive water jet machining. So this is aluminium, and we cut it from rack, like this is rack gearing. This is rack gear actually. So there is one more job of brass. Okay, this profile is called as aerodynamic profile. So our students at IIT Kanpur are working on this high pressure air. This specific component is used there. So so this kind of job also is carried out with a subtractive method of machining only, with milling machine. So this is 3D printed part, that is the outer covering of any shape. Okay, outer shell covering. So this is manufactured using vacuum forming machine. This is not with 3D printing. This is one more machine that is able to produce the outer shape covering. So So it has a specific feature in that. So this is vacuum forming machine. So with the help of vacuum forming, we can form the sheet of any shape as per our part or a die board according to that. Okay. We can make a hollow geometry, as well as 4i lab we support mechanical as well as electronics here. So in electronics we have a number of machines to fabricate and to manufacture PCBs. This is printed circuit board. Okay. You can see this is raw PCB, these are the tracks. We have etched the material from the yellow surface area, where yellow area here. This brown one is copper bead here, and then we have the chemical coating also to make it green coated at all, and copper tracks are there, and to prevent it from oxidation we use green coating, and green liquid is here to make it free from oxidation, that is green coating is happening. So this printing of white here, this printing of white material here, this is called as tin coating. To print some alphabets, some numerics, like it is showing the circuit diagram here, to clear the IC numbers that are to be put on. So we can put the what kind of soldering has to be, where the product has to be soldered. So all those symbols for transistors, symbol for ICs, earthing, input, output, then printing the kind of all the things that will be taken care within the white color, that is called as tin. So here we help the students to, or the industries, those come here to in mechanical as well in mechatronics, mechanical plus electronics. So to help our students to develop their own prototypes, their own setups and experiments, machineries. So BTech project students also we support, and we give classes, we provide training to the people who come here for the faculty development programs. We provide hands-on skill to our students and the guests who come here for learning, and support to fabricate their job. So especially support people from industries, and all those things are here.
So what we can see here is the machine is running. We can see the simulation of the machine as well as the actual machine is running here. So the simulation is happening. You will see the material is being deposited here. So all these layers that you can see as mesh here, these are supports. These supports would make the material to deposit over it. So when the machine, it has been completed on this side, now it has made one line here. So it wouldn't waste time to restart the machining from this point. When it has done, it has machining here means adding material. So when the material is added over here, it will restart from this point only and keep depositing the material here. So this is total 144 layers would be made to manufacture the part that we have designed, and estimated time here is 4 hours 32 minutes. That is the total time that is left here. So it has been an hour that we have manufactured this product. So I can pick this product from here. I'll just pick it up. So this part, this support I am removing. So the brim part is there on the machine only. So this is the final product that we have manufactured. So we can see here that on this support, the complete material deposit is not. It is only the mesh, so as the minimum material is deposited that can support the main material. That is the main filler material that is used here. So here, as we are using single spool, the same material is being used as support and main material. So these supports, you can see this was the final component that was desired here, final feature of my component here, and this is the support that is removable. So it is hollow from inside. So this is the product that we have manufactured in our demonstration in rapid prototyping, or we also call it additive manufacturing here.
So this is Tech B V30 machine, fused deposition method machine. Again, we are talking about this. This is 3D printing machine. Like we have multiple additive manufacturing or rapid manufacturing or rapid prototyping technologies like stereolithography, digital light processing, stereolithography and fused deposition method are the major ones. Then also we have laser methods like selective laser sintering, selective laser melting, electron beam melting, then laminated manufacturing like laminated object manufacturing. All those methods are there. This is a 3D printing machine. Out of the types of the 3D printing machines, this use Cartesian coordinates. There are certain types of FDM machines, it is specifically 3D printing fused deposition machining methods that use different kinds of coordinates. The Cartesian uses the x, y, z. This is the Cartesian method. Other methods are other kinds of machines are delta FDM printers. The printers use 6-axis 3D printer, which are based upon delta technologies. Machines operate with they also operate with Cartesian technology, but there is more freedom in that. Then the polar machine is there. Polar machine, the polar 3D printers. In that the positioning is not determined by x, y, and z coordinates, but by an angle, like the polar coordinate system. So another with 3D printing machine can be with the robotic arms. Different robotic arms can come and keep printing at one point. So there are major 4 kinds: Cartesian, delta, then polar, and robotic arms. So this is Cartesian FDM machine. We have gone through the demonstration of this machine in the 4i lab, and I hope you have enjoyed the demonstration, and please come up with the questions anywhere, because this was produced in 3 or 4 phases. We made the setup, we recorded the video in the lab, and then I tried to saw that video, and then I have put my voice over here. So there might be some mismatching, so pardon for that, and please come up with the questions wherever you think the things are not clear, and we'll meet in the next lecture. We will discuss further about the course. Thank you.